we're going to talk about now the standardization of sodium hydroxide using KHP, and we're also going to use that standardized sodium hydroxide to titrate vinegar. So let's jump right in. What are we going to learn? We're going to learn what standardization is. We're going to learn what titration is, how to use the dilution equation, and how to read a burette. So what's the procedure? First, we're going to make a sodium hydroxide solution. We're going to prepare a primary standard. And then we're going to prepare a burette and titrate using phenolphthalein as an indicator. And then in the second part of the experiment, we're going to prepare a vinegar sample and then prepare a burette and then titrate the vinegar sample with sodium hydroxide that was standardized in part one. So what is the standardization of a solution? Standardization is an analytical technique. If you make a standard solution, what you're making is a solution that contains a really precise known concentration of an element. And then to make that, you need a known weight of a solute, and you dissolve it up to make a specific volume. In this experiment, we're going to use KHP as our standard. KHP is short for potassium hydrogen phthalate, and we're going to dissolve that up in water. KHP is what we call a primary standard in that we can easily weigh it, has a very high purity, but the main thing is that the amount that we weigh, we can reliably assume that the weight or the mass can be accurately converted into moles, and the number of moles are reflective of that mass. Also, KHP is non-hygroscopic, which is also a great characteristic of a primary standard, because if it doesn't absorb water, the mass doesn't change, then the number of moles won't change, so on and so forth. All right, so what's the take-home message from the first section? Is that a standard, due to its accuracy, is used to accurately determine the concentration of other substances. So in this example, in your lab book, it asks you to calculate the mass of KHP that will require 15 to 20 mils of your diluted sodium hydroxide solution to reach the equivalence point. Well, first thing is we have to remember what the molarity of the sodium hydroxide diluted solution is. In the experiment, we started out by taking 4 grams of sodium hydroxide and dissolving that up in 5 milliliters of water. So if we calculate the concentration of that, then we can figure out what the concentration of the diluted sample is. Right? So 4 grams of sodium hydroxide is 0.1 moles. If we take that number over the 5 milliliters of water that it was dissolved up in, we see that the initial concentration of the sodium hydroxide of the concentrated sample is 20 molar, or 20 moles per liter. So now we have to ask what the concentration of the diluted sodium hydroxide solution is. We do that by using the dilution equation that's shown here. All right, so we'll say M1V1 equals M2V2, and all we're doing now is solving for M2. So 20 molar times, and in the procedure, it calls for us to take 4 milliliters of the 5 total milliliters of concentrated sodium hydroxide solution. So it's 20 molar times 0.004 liters. And then you set that equal to the molarity that you're looking for times 0.5, because we diluted the solution up to 0.5 liters, or 500 milliliters. Right? So if we solve for X, we see that the diluted sodium hydroxide solution is 0.16 molar. All right, so now that we know that, we can figure out how much KHP we need, the mass, because remember, for that standard, it's a solid that we're going to dilute up, right? So if we know the molarity of the sodium hydroxide, the dilute solution, and it's asking us to determine how much KHP we need for 15 to 20 mils, we're going to go with 15 milliliters. So if we multiply the molarity times the volume, that should give us the number of moles, because molarity is moles over liters, and then convert our 15 milliliters into liters, and we have a volume here of 0.015 liters. Then that tells us that we need that in 15 milliliters of the dilute solution, there will be approximately 0.0024 moles of sodium hydroxide. So therefore, if we're talking about the equivalence point, that's the point where the moles of acid and base are equal. So 0.00424 moles of KHP are needed at the equivalence point, right? So we'll say we can convert moles into grams by taking the molecular weight of KHP, which is 204.22, multiply that by the number of moles, and we see that we need 0.49 grams of KHP. That's how much is going to be required to cause 15 to 20 mils of the dilute sodium hydroxide solution to reach the equivalence point. What's the take-home message? KHP is used to standardize, or in other words, to accurately determine the concentration of our sodium hydroxide solution. So that's what we're gonna do in the next step. So the way that we determine the concentration of the sodium hydroxide is by using titration. So standardization for acid or a base, in this case, we can do that using titration, and we do multiple titrations to determine an average concentration of our titrant. So in this case, titration is another analytical technique. We use it to determine concentration. For acid-base titration, the way we determine the concentration of one or the other, it just depends on which one you want to titrate. The way that we determine the concentration is by finding the equivalence point, i.e. the point where the moles of acid and base are the same. So in titration, you have two things. You have a titrant, you have an analyte. So the analyte is the amount of precise amount of material with a known molarity or a known number of moles. So in this case, our analyte is going to be KHP because it's a primary standard. We know exactly how many moles we're using, and we can weigh it out very accurately and reliably assume that the amount that we weighed out in grams can be reliably converted into moles, and we can be certain that that number of moles are present. And then the titrant, that's the solution that we want to find the concentration of. You determine that based on the analyte. Right? So titration is usually done using a burette containing your titrant and a beaker or Erlenmeyer flask containing your analyte. And you titrate the titrant into the analyte dropwise, 1 to 2 milliliters at a time, depending on what you're using. Right? So titration is also usually done with an indicator because you can't visibly see the endpoint or the equivalence point of the acid-base reaction. So you need some type of indicator. And in our case, we're going to use phenolphthalein. All right, so this is KHP shown here. It's going to react with sodium hydroxide and give you this phthalate salt plus water. All right. And if you note, there's a 1-to-1 ratio of H plus and OH minus, right? Because there's only one proton on KHP shown here, and then one OH group in sodium hydroxide, right? So this is how the mechanism of the reaction, this is the mechanism shown here. So we have sodium hydroxide that's going to give a pair of electrons to the pink hydrogen on KHP, and that's going to do what's called proton transfer. And then you break the OH bond. What you're left with, the phthalate salt shown here on the right, and water. And so what we know about KHP, we say that KHP is monoprotic, meaning that it has one proton to give away. It's a monoprotic Bronsted acid that reacts with sodium hydroxide, which is a Bronsted base, via this proton transfer reaction. All right. So here's my titration setup. So what I want to do is add in my titrant into my analyte. There's white paper underneath the Erlenmeyer flask so that you can see the color more accurately. And as I add it, I also see here on the right, at the end point, there'll be a color change because the analyte contains an indicator. Okay, so the analyte contains an indicator, and at the end point, color changes, and that's how I know when to stop. And then after that, I need to measure how much sodium hydroxide I put in. So I want to look at my burette. And I also, when I look at the burette, notice the solution is in water. So there's a slight curve downward. And that curve is called the meniscus. We always read our burette from the meniscus. And we read it as close as possible based on the gradations between the units or the numbers on the burette. Right, most burettes are going to be in milliliters, and so we're able to read here, so we can accurately say that this is about 41.25 milliliters. right? Because the 41 is here, and then there's 0.1 per every gradation. And so you can see the meniscus is about halfway between the second and the third gradation. So we can say it's about 41.25. All right. So we're going to repeat the KHP experiment twice and then determine the average concentration of sodium hydroxide.